buffer calculations. We've just recapped how buffers work. We've recapped how you make a buffer. I'm going to focus on acid buffers particularly, and we'll come back to basic buffers as well. So buffer calculations. So I'm not going to talk about basic buffers at the moment. We're going to do plenty of other ones. So we're going to use the packs that you've got to help us. But what I told you last time is some stuff which is going to be we're going to use today when doing these calculations. So last time we talked about the fact we know already that Ka for a weak acid is equal to H plus concentration times A minus concentration divided by HA. Now for a weak acid, just remind you, for a weak acid, H plus is equal to A minus, and so we write H plus squared there. But this is not a weak acid now, this is a buffer. So in a buffer, H plus does not equal A minus. Okay, so we've got to reset our understanding of how we use this equation, right? So it's not the same as weak acid. Do not get those two things confused. I also showed you last time, and this is not in the syllabus, but I think it helps me to understand what's going on. We said that pKa is equal to pH. We took the log of both sides minus the log of A minus over HA. And we can rewrite that to say pH is equal to pKa plus the log of A minus over HA. We used that last time to help us understand why the pH at half the equivalence point is equal to the pKa. Is what we did last time. Okay, and I'm going to check that you've done the work I've asked you to do on that. I don't remember setting a deadline on it, so I might have to just see where you're at with it. But I do want you to complete the work that I set you last time if you haven't already at some point. But at that half equivalence point, pH equals pKa. Also, little recap, always worth recapping stuff. At the equivalence point, we've got a weak acid and a strong alkali. We've got the salt. That's the point at which you've added an equal number of moles of acid and alkali. So we've generated the salt. For a weak acid and alkali, is the pH greater than 7 or lower than 7? Please point up or point down. Greater than 7 or lower than 7? We can explain that by doing what, please, Lewis? How can we explain that salt is basic?
Because at the weak point, the A minus and HA are equal.
They are equal, yeah. So we've generated, say, for example, sodium methanoate. Sodium methanoate in water generates a pH greater than 7. So what must be produced? What must this produce to have a pH greater than 7? OH minus. Remember that, you can get to the answer. So how is OH minus generated from the A minus? What is it that A minus reacts with to generate OH minus? Plus something goes to OH minus plus HA. What's in that pot? What is there a lot of in that pot that A minus reacts with? Well, the answer is water, isn't it? Yeah, I think lots of you know. You got the feeling of being put on the spot there, and I apologise. It's Friday morning, right? So we generate hydroxide, don't we? All right. So what I want you to do, just want to point out to you, can you just get your booklets and turn to page 21? I just want to highlight to you that there are some good notes here that will help you. You can refer to and revise from. We're not going to do an assessment on acids before the mock, but we're not a million miles away from finishing this topic. But there's a whole lot of great stuff in this book explaining what a buffer solution is, examples of buffers from acids and alkalis, how you make buffers is all on that first page that I'm showing you now. And there's the explanation of how buffers work. So an acid buffer, when we add H plus or OH minus, is what we've just talked about. There is this extra point in A-level syllabuses about what happens when you add water as well, so that's in there. And there's a whole load of stuff about how basic buffers work, and it all fits together, it all aligns. So just you've got some notes there on this if your notes aren't great. Worth pointing that out to you. But what we're going to do is learn how to calculate the pH of acid buffers. And so there's a nice worked example or two on page 23 as well that you can refer to. But I think what we'll do, and 24, that there's 4 examples for you to work through there. But we're going to have a go at one of these together, and you're going to see maybe a couple of ways of approaching it. So we're going to have a go at doing question 1 together now. So the first thing is calculating the pH of a buffer, but it could be you asked how to make a buffer as well. So there's 2 possible ways of asking questions here. All right, so the first question is relatively straightforward. We're mixing a weak acid with its salt. Okay, we're mixing a weak acid with its salt. So the weak acid is methanoic acid. We've been given the Ka. The number of moles of this weak acid is, we can work out simply by doing 50 times 1 divided by 1,000, which is 0.050 moles. So we know that. And the number of moles, we always work out the number of moles. We've got number of moles of sodium methanoate. So is equal to 20 times 1 divided by 1,000, so 0.02. Okay, so it's worth working out the number of moles to start with. Now, we are going to use either one of these 2 equations at the top here to solve it. Now, I think I'm going to point you to and encourage you to use this is the one that we're going to use. This is the simplest way to do it. So we need to know the pH, which means we need to work out the H plus concentration. We know the Ka. We need to work out, therefore, the A minus concentration and the HA concentration. That's what we're trying to get towards. HA is sodium methanoate. A minus is sodium methanoate, and HA is the methanoic acid. So we know the number of moles. We're going to be careful with here is we need to know the volume, total volume in each case. The volume is the total volume of both solutions. We've got the volume of water is 50, add 20, which is equal to 70 centimeters cubed, right? So we can work out the concentration in each case. So the concentration of methanoic acid is moles divided by volume, isn't it? 0.050. I'm going to do the volume in decimeters cubed to keep it a little bit easier, to save me timesing by 1,000. 0.070. Someone could work that out for me to save a little bit of time. That'd be really helpful. And leap if I make a mistake, which I'm probably going to make. This is I suppose the most difficult bit of all is realising the volume is 70 to work out the concentration. Someone could tell me the concentrations of each other, that would be smashing. Someone tap those in. Five over 7, that's all we need, whatever that is, and 2 over 7. 0.714, and this is, could have worked that out, couldn't I really, because they add up to 1. And so you plug those numbers in to the rearranged Ka equation. So I'm going to rearrange the Ka equation. So H plus concentration is equal to HA concentration times by the Ka, which was given in the question, divided by the A minus concentration. I'll remind you at this point that the pH is dependent on the ratio of these two concentrations here. Some people might have spotted a shortcut, which I'm deliberately not highlighting. Those maths geeks amongst you might have spotted that. I'm not going to worry, we're just going to work things out properly. You know what I'm talking about, probably some of you. But if you can just tap those numbers in for me using the Ka as given here, you should find you'll be able to work it out. So tap those numbers in for me and see what we get. We can check. So 1.78 times 10 to the minus 4 times by 0.714 divided by 0.286. So we need
4.44 times 10 to the minus 4.
and if you do minus the log of that number, Tom.
3.35.
And does that feel right? Well, is it an acid buffer? Yeah, it absolutely is an acid buffer. Now, it's worth being aware of, if this is a useful thing to kind of get a sense of, a buffer is the pH of a buffer is going to be pretty close to the pKa of that weak acid, usually in that. Is that right? It's going to feel that feels like kind of about right. But someone just confirm those numbers for me, please, Isabel? You got the same numbers? We'll just check those in the back, make sure we've done it right, and then I'm going to highlight a couple of things that are different in other questions. So we've got the right answer. Hooray! That's a relief. The second question is almost exactly the same, except we've got to convert from pKa to Ka. So I'm not going to do that with you. The third question, 1C. I just wait just for a sec, please. The third question is slightly different because we're using solid potassium ethanoate, so we've got to work out the number of moles of potassium ethanoate and work out its concentration using the volume that's there. The concentration of ethanoic acid is already done for you, so that's easy. Now, for question 2, it's a bit more difficult. So let's have some eyes this way so you know what you're doing here as well. So the second ones, you've got to be really careful with these questions. For question 2, you've got to be really careful with. And this is, the one that we stumbled on a couple of weeks ago. This is what was going on. So if you add sodium hydroxide, I think it is, sodium hydroxide to methanoic acid, you need to work out the initial number of moles of methanoic acid. But when you add sodium hydroxide to it, the number of moles will go down a bit, of course, because we're using some of it up. And also you're making some sodium methanoate. So we can do that question actually. Why don't we do question 2A together, and then you can just go, I'll let you go at your own pace after that. So number of moles of methanoic acid. Sometimes worry about holding you guys back, but actually I think we'll just do this one together. Number of moles of methanoic acid is 25 times 0.5 divided by 1,000, which is 0. I think it's that, but someone could just check that for me, please. The number of moles, that's the initial number of moles of methanoic acid. The initial moles of sodium hydroxide is 10 times 1 divided by 1,000. So I know how much I started with, and the reaction they're going to do is simply a deprotonation. Neutralization, but it's not going to completion because I've got a limiting amount of sodium hydroxide, which means I'm going to have some of this remaining. They react in a 1:1:1:1 ratio, keeps it simple, and I've worked out the initial number of moles of both of them, so 0.714 0.125, 0.010. The change in moles. All of the sodium hydroxide is going to be used up, right? Minus 0.010. And minus, we're also going to use up the same amount of the methanoic acid. And we're going to generate that many moles of sodium methanoate and water. And so the final moles, which is going to be important, is that take away that. Then you've got to work out the concentration of each one using the total volume of everything we've got, which we go back to the question, 25 and 10. So the volume equals 30 centimeters cubed. So we can work out the concentration of methanoic acid and the concentration of sodium methanoate by dividing number of moles by the volume in decimeters cubed. And then you just plug them. I've made a mistake. You can, a few of you got your hands up. 35, thank you. Thank you for this pointing out and pointing out. Volume is 35. Why did I write on 30? I just said 35, didn't I? I think I said that. Well, I'll play it back later on. I'm pretty sure I said 35 and wrote down 30. Thank you for doing that. So there we go. So you can work out 25 into 35 and 10 into 35. And then plug the numbers in just as before. So I might stop it at that point for now. Some of you might be thinking, well, am I not supposed to include the water that I've generated as well? Surely that's going to add a little bit of water. By all means, work out what volume of water that is. I mean, I can do that for you because I know that 1 mole of water is 18 centimeters cubed. So it's 0.018 centimeters cubed, which is negligible, which won't change the number. So don't worry about that. You know, the IB are quite good at this. They might spotted it and put it as one of their alternative answers. Please don't worry about it here. It won't be counted. Okay. So if you can carry on and work out the concentration. Someone do that for me. 25 into 35. Yeah, you got it. No, you got it, Freddie? And 10 into 35. Oh no, it's not. It's 0.0025 into 0.035.
Yeah, so that I've got 0.071.
Yeah. And the other one? It must be 0.029.
Yeah.
And then you plug those numbers in. Yeah? Happy with that? If you're wondering how I got to 0.029, well, the denominator is the same. That was my little clue there. Right? So they had to add up to 0. Or whatever. Carry on. And have a go at doing some questions yourselves now. Right, I'll stop this and share with the absent parties.